In this video I want to pay attention about how to do experiments with analog electronics. I tell that it is part 1, but perhaps there is no part 2, etc. etc. I found out and descripted, say, a few first ideas, only ideas that have to be taken in account when you do experiments with analog electronics. And here some ideas. Search between the electrodes where you can expect effects, and then I mean effects in terms of voltage, frequency or duty cycles. I published this circuit today with the 555 voltage controller, voltage controlled oscillator, and in that circuit there are here, for instance, 2 wires connected between the pins. You don't have to expect any effect when you, for instance, solder over that wire a capacitor or a resistor anyway. Everything to do with Ohm's Law, with the fundamentals of electronics, etc. So on such a circuit there are pins that are active. So they make a change in the frequency or whatever when you connect another voltage, another capacitor, another resistor, etc. So that's important. And the second important thing is regard Ohm's Law. Voltage is current multiplied by resistance. What is voltage multiplied by the current, ampere? Also always important, limit destructive currents. That means that when you want to do experiments, for instance in such a circuit, I take it only as an example, when you make connections between these pins and try to get to other results, make the resistance value not too low, because otherwise you have a shortcut. That can damage not only this chip but also many other circuits. A good idea is always to connect the output to the input, also very interesting. And I've talked about that in the earlier videos and in many other videos on my YouTube channel. And what does it mean, connect output to the input? Well, I will give more information later, and use semiconductors that can handle the voltage and the current. That's very important. Many, say, small signal transistors cannot handle a too high current, approximately higher than, say, 30 volts. Of course, the data sheet is the most important thing to take conclusions. And also important, in many transistors are not able to handle a higher base voltage compared to the collector emitter voltage. That's important. Only, as far as I know, the transistor that I always use is the BD139 and the BD140. They can handle a higher base voltage compared to the collector emitter voltage. And there's much more to tell. The second breakdown phenomenon, etc. etc. So, I want to make some drawings. At first, regarding Ohm's Law. Regard Ohm's Law. Important. Say you have a circuit somewhere, and there is a point here in that circuit, electronic circuit, and you want to send a signal back from the output to the input, and want to do that via a resistor. It's always very important to watch what voltage is here available and what is the impact. How high is the current that can flow from the output to the input. That can be calculated with Ohm's Law, and the good idea, for instance, is to be conservative. I don't want to go too deep because otherwise my video will get far too long. Say this is an amplifier. Here we have the input and here we have the output. Say here's a loudspeaker connected to the output of that amplifier, and here we send in 1 kilocycles, 1000 Hertz. What will be the effect when you connect a resistor from the output to the input? Well, that's more or less unpredictable. Has everything to do with the circuit, but when this is, for instance, a transistor amplifier on 12 volt, here's the positive, and here we have the negative. Connect the resistor from the output to the input. At first we have to do with Ohm's law, the current that can flow in such a circuit can be far too high. So when you do such an experiment, take for instance 100k or 47k, good value, and then study the effects. And you can do that of course with the scope. Very important, always connect your scope, use your scope and see how that will work. Send in 1 kc, send in study how that effect will be. A resistor is not frequency dependent. That means that we, in such a case, in many circuits, you get a current flowing here, and there is no frequency dependency. That means that you could get a kind of damping. It could change the output level, but more important, for instance, when you use in this case a capacitor, this is a time dependent circuit. It's an RC circuit. That means that certain, and when this is not 1 kc but say audio, 20 Hertz to 20 kc, and you send a part of the signal back to the input. This is frequency dependent unit. That means that it's made to oscillate on a certain frequency when you test that in an oscillator, and when the phase is correct or not correct, the whole circuit will start to oscillate on the most important part of the circuit is this. This will set the frequency, but also the parasitic frequencies, etc., etc. So, in another way, when the phase is connected in another way to the audio amplifier, for instance here somewhere, I have to call it somewhere, and my knowledge is experimental, and that's why I tell it in this way. It could be that it does not oscillate, but it limits the frequency band of the amplifier. Say this is 1 Hertz and 20 kilohertz. That combination here has an effect on the frequency band. So here the amplification is at its utmost. That depends of course on the resistor value and the capacitor value. That's completely normal. And of course you can study this in a more or less scientific way with calculations, etc., etc. But this is a hobby channel, so I explain it in this way. This makes that amplifier frequency dependent. That's important to tell. It also, in many cases, and you can see that in classic transistor circuits, transistor amplifiers of the 1970s and the 1980s, and the principle is universal, by the way. It also limits in many cases the audio distortion, because it corrects the current that flows here out of the output to the speaker, corrects in a certain way directly the changes of voltage at the input. So we have here, for instance, a music signal that consists of all kinds of sine waves, and by coupling a part of that complex music signal back to the input, we can bring back the audio distortion. Come it out. That was all. Of course, there are many better circuits, explanations anywhere, but this is the pure experience of approximately 50 years of making audio amplifiers. In general, let's look at an amplifier. This is an amplifier. And here we have a positive and here we have a negative. That could also be reversed, but that is not very important. Output to input, well, I have explained it. Capacitor or a resistor. That is more or less the principal circuit. So that's a good way to do an experiment with an analog circuit. And inside such an amplifier, this looks like a kind of block, but in most cases we have here, for instance, the first transistor, the second transistor, the third transistor, be it soldered in, mounted in whatever way. And of course it depends very much when you send the output signal to the first transistor, so here, to the base has an effect, to the emitter has an effect, and also to the base of the second transistor has a certain effect, to the emitter of the second transistor has a certain effect, the third transistor, this is often a complementary end stage, but all these connections have different effects that differ on what say position or stage of amplification the audio signal is. So in the first transistor it's often amplified perhaps 100 times, could be 100 times. And when the transistor is biased properly, there is a real good sine wave here. On the second transistor, it could be that it is amplified not 100 times, because that's a lot. When we have 0.8 volts in, 0.8 volts multiplied by 100 is, well, that's of course not real in a certain way, but anyway, this transistor has in general another bias. That means that the way that it amplifies the audio signal differs. And that means also another effect of coupling back the output signal to somewhere inside this audio amplifier. My camera runs out. Thanks for watching. It will be perhaps a sloppy video, but I only wanted to give some ideas about how you can do experiments, and this could be part 1. And perhaps other parts will follow. Thanks for watching.